algebra. So you remember in the algebra that you learned, whenever we had one function, usually we actually show the function like this, right? We say, okay, y is the function of the x. So usually you define the domain and the range. So in algebra, we have domain and range for any function like this. So could anyone actually tell us what's the meaning of the domain? What is the domain of the function, what it means? We had domain and we had range, right? So for example, I give you example, maybe it's help to, if you have a function like is y equal to x, so what is the domain and range for this function? Remember that from algebra class. It means domain and range. So the domain actually tells us the set that x able to get, right? Domain is positive y and x. Yeah, definitely. So it means whatever you could actually replace by x. If you say domain is the real number or r, okay, so that means the x could be get any values from the real numbers, right? So that means you could put 1, 2, 3, negative, all things that you have in the real number sets, okay? So in the other side, you have a range, okay? What range means? So range means if you give each of these value from the R, so which value y able to get. So for this specific example, the range is R, right? So that means if x is able to get any value from the real number, so the y also will be actually the real numbers too. You actually put the real number, which is the r. Yeah, the r could be any number from infinity to positive infinity, okay? Whatever you have, positive number, negative number, whatever you have in that range, consider as a real number, okay? So, but we have the same thing in the Boolean algebra. So suppose right now you are in Boolean algebra and you have the same actually function, not same function, I represent with y equal fx. So in the actually the Boolean algebra, there is limitation for the domain. So that means what number we could actually replace with x. Again, let's have the same example, okay? So not same example, maybe the other example, because this couldn't be in the Boolean algebra. Let I tell you this. X actually dot x, okay? Or equal, it could be x, it doesn't matter, okay? So x, okay, x dot x, which is we will learn about that later. It could be equal to x, unlike the other, actually the normal algebra that we have. Okay, for now, just consider you have a function like this. So you tell me, could we replace x with any numbers in the Boolean algebra, which is the same with the base 2? So the answer is no. In the Boolean algebra, the only domain that you could have is 0, 1. Whatever you see as a variable in the Boolean algebra, you couldn't actually get any value that you want. The only option that you have is 0, 1. So that means each variables in the Boolean algebra just able to get two values. The first one is 0, the next one is 1. Same thing for the range. So whatever these y able to get is exactly just the 0, 1. It couldn't be get any other numbers, okay? For example, if you give 1 and 1, this means we actually read that as an and, right? So we say 1 and 1, so you have 1, okay? So the only operation that you have in the Boolean algebra is that's operation that we learned whenever we talk about the gates, right? We had actually the and, or, XOR, not. So these are actually the only operation that we have in Boolean algebra, okay? So just consider this. So that means in the Boolean algebra, the function, the domain just able to get the value 0, 1, and the range again just could be 0, 1. This is unlike the normal algebra that you learn, which is usually you could get the R or N natural numbers or real numbers for your domain and the R, okay? So we keep this in our mind and go and review the Boolean algebra postulate. So any actually, even in the normal algebra that we learn, we have some postulates. A postulate means these are some principles that you accept without proving that, okay? So title, we want to talk about the postulates of Boolean algebra. So the postulate actually is a concept that you accept without actually proving them. So what is the first one? So the first one is this. The first one is the x plus y equal to y plus x. Okay, so this somehow is obvious, right? So we have the same thing in our regular algebra. If you say 2 plus 5 equal to 5 plus 2, okay? So here we have the same thing. The second thing you accept without actually any proof is x minus y equal to y times x. Just be careful. Whenever you are in algebra, this dot means and, this plus means or, okay? So this is, we say x or y or x. So it should be read like this. X and y equal y and x. X or y equal to y or x, okay? So this is the Boolean algebra and you have its own operation, okay? For today, so this is actually the second one. So if you say x and 1 equal to y and x, which is you already know, what should be equal to, should be equal to x. So that means if you and anything with 1, so it's somehow you will be return the value of these x. If x is 0, it should be 0. If is 1 is 1, okay? So in other words, you could say 1 and x and 1 equal 1 and x equal to x, which is somehow is obvious, right? So how about this? X plus 1, which is we read in Boolean algebra, x or 1 equal to, definitely if you use the first postulate here, you could say should be equal to 1 plus x. Based on what you learn on the lab, could you tell me it should be equal to what? 1 plus x. If you say, if you OR anything with 1, what you will get should be 0 or 1. So remember from truth table of the OR gate. So if you OR anything with 1, yeah, definitely should be 1, right? So 1. So let I actually give you remind you of the OR gate truth table. You verify this table, right? You say 0, 0, 1, 1, 0, 1, 0, 1. This is or 0, 0 is 0. 0, 1 is 1. 0, 1 is 1. 1, 1 is 1. So this is a truth table of the OR, right? So could I tell if I OR anything with 1, which is here I put OR 1 with 0, I got 1. Here I OR 1 with anything, which is here again is 1. So here you have both 1 is 1. So that means whenever one of your inputs is 1, no matter what's the value of the second, definitely the output is 1. So that's what you see from the truth table of the OR, and also that's a postulate from Boolean algebra. Somehow you already know that whenever you learn about the truth table of the OR, okay? So if you have any question in any part, you could actually interrupt me, that's fine, okay? So let's go to the 3. We just accept this, okay? So These are one couple of the postulate which is right in Boolean algebra. So the next one somehow is not obvious. If you say x or x and y, okay, so it's equal to x. And the next one is if you do this, if you say x actually and x or y, again it's equal to x, okay, which is somehow it is not obvious, but it's working that way, okay, we accept that. So number 4 is this. If you take 2 times not, so that means x prime, which is the not, so this is not. So if you actually take 1 times not of one variable and again takes another not, so it's equal to what? Based on what you learn from not gate in the lab, you should be able to tell us what should be the response of the right side, what should be having right side. So if you take the not 2 times from one variable in the Boolean algebra, it's equal to x, right? Why? If you say 0 not is 1, again take actually not from that, which is should be 0. So that means it's equal to the origin value of the x, okay? So here we actually have that as a postulate of the Boolean algebra, okay? You need to somehow remember these. So this somehow one is obvious. So for me, the number 2 is obvious. So number 3 is something you need to remember. And number 4 is somehow you already know from the truth tables that you learn in the lab section, okay? So just consider these 4 as a postulate, which is means we accept them without any proof. So, but in the other side, you have some actually the theorem, okay? So the next actually things that I want to mention, let's to write the title. So the title is the theorems of Boolean of Boolean algebra. So technically, whenever you say theorem of the Boolean algebra, the theorem must be proven from the postulate. So you accept these 4, whatever we have here as a theory, you could find a proof in the book, okay? I'm not going to prove them here because I don't want to somehow take our class time. We just use that theory. We don't care how you could prove them. But if you are interested to see how you could prove, you could take a look to the book. So let's just see how many we have. So we have actually few of them. So let's just change the color. So let's actually get more space here. Okay. So number 1, you could actually prove based off that 4 postulates. So in the Boolean algebra, if you add 2 variables, same variable, x plus x, unlike the normal algebra, which is you say x plus x is 2x, so here x plus x is x. Okay. So same thing for x and x. Here is not x power 2, here is x, which is somehow, if you again take a look to the truth table of the and or, somehow it is obvious. Why? If I say 1 or 1 is 1, right? So x is 1, you say 1 or 1 is 1, which is the x, right? If you consider x as a 0, just be careful. You are in Boolean algebra, the domain and range is just 0 and 1. So that means here x couldn't get 2, couldn't get 5. The only things here x, y, or any other variables able to get is just 0 and 1, okay? So I test one of them, which is 1 or 1 is 1. That's right, so it is works. The next one I put the x as a 0. 0 or 0 equal to 0, right? So that means it works, right? So the same thing for and. If you say 1 and 1, again is 1. So that means x. If x is 0, if you say 0 and 0, again is equal to 0, okay? Somehow it's obvious, okay? So this is actually the theory number 1. Let you go to the 2. So in 2, you have actually this. So if you say x and, so see, I'm actually read whenever I'm writing, I say x and, this is and, okay, and 0 equal to the same thing, you say 0 and x based off these first postulate. So it is equal to what? You tell me. You should actually, without I telling this is the theory, what should be this side, based off what you learn in the lab with the truth table of the and, you should tell me what should be equal to what. If I and anything with any variable, what's the result? 1 or 0? 0 and any variable. So here I need to refresh what you learn on the lab. So see, this is the truth table of the and, right? 0, 1, 0, 1, 0, 1. This is z. So we actually say this is 0, this is 0, this is 1, right? So this is a truth table of the and. So you tell me here, consider one of them. So see, if one of them is 0 and this 0 with this 0, you got 0. Here you add this 0 with this 1, again result is 0. Here you add this 0 with this 1, again result is 0. So just whenever the both of them is 1, it is actually 1. So that means if you add 0 with any variable, the answer is 0. Okay? So there is for the proof for that in the book, but we actually just use this format that you see. If you add the 0 with anything, any variable, the result is 0. Somehow you already actually saw that in the truth table of the and, okay? So similar with the first one, this is another actually theory that we have. If you say x plus 1, actually that's better to not tell 1, not plus, we say or, okay? So let I raise this. Okay, so if I back here. So if I say, so see, I'm reading in the right way. X or 1 equal to 1 or x. You tell me it should be equal to what based off the truth table of the or. So that I refresh your mind. So this is a truth table of the or that you learn in the lab. This is x, y, this is z, 0, 0, 1, 1, 0, 1, 0, 1, okay? So remember in the OR gate, so whenever one of them is 1, the output is 1. Whenever the both is 0, that's a 0, okay? So see, whenever one, you OR here, so check this, okay? So here you OR 1 with any variable, which is here is 0, the output is 1. Here again, you OR this 1 with this 0, again you got 1. Here you OR 1 with 1, again you got 1. So that means if one input is 1, no matter what's the value of these x, if it's 0 or 1, definitely the output will be 1, okay? So somehow it's obvious, but you need to remember that in the Boolean algebra. So that means if you AND anything with 0, the result is 0. If you OR any variable with 1, the result will be 1. Number three is this. If you say x or x and y, it should be equal to x, and also x and x plus x or y is equal to x, okay? So this is actually what did we mention that in the postulate or? Yeah, so see, I actually did a mistake. It should be whatever you have here as a number 3, which is exactly the same thing. Somehow I mixed these two. So as a third one, this is a theory, not postulate. So let I fix that. So number 3 for the theory should be this. So let I actually fix this. So it should be x time x prime equal to x prime dot x equal to 0, and x plus x prime is x prime plus x is actually 1. Okay, so which is, for us, it doesn't matter that's postulate or theorem. You need to actually know these are actually what we have in the Boolean algebra. Okay, so this new one that I add as a postulate, which is somehow I mix with number 3 in the theory. So it says if you and, so see how I'm reading this. If you have one variable here on the Boolean algebra, if you and that with its not, the result will be 0. So you just could put some value here, 0, 1, as see if it works or not. You say, suppose x is 1. So if x is 1, what is the x prime if x is 1? If x is 1, what is the x prime? Just type on the chat box. If x is 1, what is the not of 1? You actually did that in the lab. So it's 0, right? So you say 1 and the 0. What is the 1 and the 0? If you and anything with 0, the result is 0. Okay, so that's what you have. Somehow is obvious. So see the next one, x or x prime equal to 1. So let I just put some value. If x is 1, you say 1 or 0. What is the 1 or 0? Type on the chat box. 1 or 0. 1. So see, it works. So you consider x as a 0 if you don't like that. You say x is 0, x prime is 1. Again, what is the 0 or 1? Again is 1. Okay, somehow is obvious. Okay, so back to actually the theory, which is the third one, is that what I already mentioned in the postulate, which is x or x and y is x, and x and x or y is x. Again, there is a proof for that in the book, but we use as what you see on the notes. So this is actually number 3. So number 4. So number 4 is again somehow obvious. So yeah, definitely. I don't know why I mix all of them. So number 4 is actually is whatever I put on the postulate, which should be here. So I already explained x prime prime is x, which is number 4 in the theory. I'm going to fix that, and number 4 for postulate is the other thing. So is whatever you see here, which I'm going to correct that. Okay. So number 4 was this for postulate, x dot y or z equal to xy or xz, which is somehow we have exactly the same thing in the normal algebra, right? So x parentheses y and z equal to x or y and also dot x or z. Okay, see, so the first one as a number 4 for postulate is this, which is somehow obvious. So you could actually distribute these dot inside these parentheses. You are doing the same thing on the normal algebra, right? So here it's actually working the Boolean. So x dot x and y or z equal to x and y, or x actually or x and z, which is same thing that you have in the normal algebra. You have the similar things for the or, and you could distribute or inside the parentheses, which should be x or y. You have the first sentence, so then you have these and then x or the z that you have. Okay, so this is actually is number 4. So back to here, technically number 4 theorem is this: x you take 2 times the prime, it's equal to x. So for now, we just read this. We will have the example, which is you actually see why we are actually having all of them. Okay. So any questions so far? So let's go to number 5. So let's check the chat box and see if we have any question. Okay, that's good. So let's go to number 5. So that's actually 7. We will have the totally 7 of them. So let's do back here and see what is the next, which is we label that as a number 5. Okay. So number 5 is this. This is actually x or with x prime y equal to x plus y. So this is somehow not obvious, at least. X dot or and with x prime plus y equal to x and y. So again, their proof is on the book, okay? We just use them, okay? So if you say, if I want to read that in the right way, you need to say if you or the variable with the end of the other variable with its not, it should be actually that variable which is x or with y. So similar things for and x and x prime plus y equal to x and y. So there is a proof for that, so which is in the book. We just use in this shape that you see. This is number 5. So let's actually have number 6, which is number 6 is we have the same thing in the normal algebra that we have. So x plus y plus z, which is that's better to say x or y then or with z equal to x plus y plus z. You have the same thing on the normal algebras, right? We call these associative features, right, or properties. So this is similar. We hear its work. So you have the same thing for the and x and y. If you and x and y, then the whole thing and with z, you could actually, it's equal to x and y and z. Okay, so which is this is actually, there is a proof for that again on the book. If you are interested, you could take a look. So let's have the last one, which is number 7, which is the De Morgan theory. Okay, it says if you actually have this, which is x and y, then take the prime of this, or take a not of x and y. It's equal to x prime plus y prime. Okay, so if you do this first or two variable, then take a not, it's equal to actually the first one prime, then actually and y prime. So this is actually is famous to De Morgan theory. Okay, De Morgan theory. Okay. So these are actually is the 7 theory and also 4 postulate of the Boolean algebra. Why we have this? We use these actually 7 theory and 4 postulate to make the function as much as simple we could. There is a reason for that. You try to simplify the Boolean function is actually important topics in the digital design. There is a reason for that. Whenever you actually don't simplify the function, whenever you implement that, you need probably too much gate to implement that. But whenever you simplify that, probably you need actually less gate, which is the circuit is exactly same, doing the same thing, but you actually use the less gates. So you will see that. We will talk about how you could simplify the Boolean algebra or Boolean function, which is the main topic of this chapter, which is chapter 2. For now, just consider in Boolean algebra, you have 4 postulates. You just remember that, okay? And also 7 theory, which we will use them whenever we want to simplify the function or simplify the actually Boolean function. Okay.